Good evening, everyone. So previously you have seen primarily how the wave is propagating through the discrete metamaterial. We have seen undamped case, we have seen damped case, and we have also plotted the dispersion diagram. We have identified where the attenuation bands are happening, what is the effect of damping, and different types of the cases like negative mass in mass metamaterial, negative stiffness, inertial amplifier, negative stiffness, negative mass inertial amplifier, all combining. Also we have seen which is a generalized monoatomic chain. So that portion we have done. Now we are looking forward to go for the continuous system. So there, instead of solving like a discrete spring mass condition, now we are going to solve for continuous system. So there we will solve the PDE and all. So the first case, if we see, that is our beam. So sorry, bar. So like we have a Euler-Bernoulli bar. So sorry, we have a bar equation. So if we just take a single portion of that bar, so you can say that area, the cross-sectional area of the bar, is A, and Young modulus is E, density is rho, okay, and length is L. So our first target is to establish the stiffness matrix for that, like if we are applying a force in the left side and right side, and how much the displacement. So what should be the stiffness matrix in terms of the frequency domain. So let's see, can you able to write it or not. So if we think that we take a element, internal element, and if we think that we are applying the force like this is F and this is F plus delta F, the element is dx, area is dA. So how much? So now if we are doing the force balance, we can write F plus delta F minus F should be equal to, you will get a mass into inertia, that is U double dot. So m into U double dot, m into U double dot, not dx, not dx. Now mass is how much? Rho is the density, and A is the area, and dx is the length. So you can say rho A dx into U double dot. Okay. So that is delta force equal to this much. Now what is the delta force? There is a change of the force. Now that change of the force will create the extension in that portion. So how much extension it will create? That will EA divided by dx. So so if I think like, sorry, epsilon will be equal to area into stress. Agreed? Area into stress. So what is stress? Stress will be nothing but Young modulus into strain. What is strain? That will be, so if I just think, that will be EA into del U del x. That will be strain. So what can I write? EA what that small area should be equal to rho A. This one is the force, that is all okay, yeah. Equal to rho A U double dot dx. Okay. So from here, what can we write? EA into del 2U del x2 equal to rho A u double dot. And from here we can see this is the equation of motion for a bar. So here we can see u. So u is what? U is the displacement field within the medium. Okay, so it describes that how the displacement field is getting evolved with displacement, with the distance and with the time. Means how it is get evolved in the space and time. Okay, so now if you think that, so u is basically a function of x and t. Simple, u is a function of x and t because it is varying with space and it is varying with time as well. So if that thing is happening, now our objective is primarily to solve this equation. So what is the type of this equation? This is second order partial differential equation. Why it is partial? Because it has two independent terms, x and t. Okay, so that's why it is partial. If you see, our discrete system was ordinary because it's an ordinary differential equation. It is giving the ordinary differential equation. There the space term was not explicitly present in the equation of motion. That was there in terms of, like, we have the distances, and once we are writing the equation of once we are applying the Bloch theorem, then that was present. But in the equation of motion, that was not there. But here in the equation of motion itself, you can see the presence of the space explicitly. Clear? Okay. So in this case, what is the way that how we can able to solve a partial differential equation? What is the very standard way to solve the partial differential equation? Variable separation is the correct way to do that. So you can assume that this has the two function, means it is dependent on x and t. So you can think that I am writing whatever it is in that way, that it is something like, you can think that u of x into maybe g of t. Okay, so you segregate that two. U of x is primarily the function of x only, and g of t is primarily the function of t only, and their product itself is your complex function, means complicated function is coming by that two way. Okay, that is known as the variable separation. So you separate the variable from this. Okay, so now if you think here, what is happening? So now if I am just substituting here del 2u del x2, what can I say? I will just do the 2 times derivative on this, and this will remain constant. Okay, and if I do this thing, this will remain constant and it will be double derivative of t. Make sense? Very good. So if this is agreed, and now we can think that, we can assume that, if you see in the last case what happened, once we are plotting the dispersion, we were exciting the structure with a harmonic excitation. So here also, if we think that structure is excited by a harmonic excitation, and we will look the primarily the steady state vibration, so what will be the nature of the g of t? G of t will be harmonic. So can I write that g of t equal to e to the power of I omega t, or omega bar t? Omega bar is the excitation frequency. Can I write it? Yes. If I can write it, then look, what will be the g double dot t? Minus omega bar square e to the power of I omega bar t. Agreed? Simple. Now if we are substituting this full thing here, what can we get? What we are substituting? We are like writing like this is maybe 2, 3, 4, 5. So if I am substituting like 2 to 5 into 1, what can I write? EA U double dash X into e to the power of e to the power of I omega bar t minus omega bar square ux e to the power of I omega bar t, that is equal to 0. Sorry, there will be rho into a. Agreed? Perfect. So now you can obviously see that e to the power of I omega bar t can be cancelled out, or maybe you can just say that like EA U double dash X minus omega bar square rho A into UX. This full thing is multiplied by I omega bar t, that is equal to 0. And definitely e to the power of I omega bar t is not equal to 0. There is no doubt on that. So you can say that this portion is equal to 0. Agreed? Agreed? That this part is becoming 0. Now let me just rewrite that portion. So you will writing EA U double dash X minus rho A UX omega bar square, that is equal to 0. No, very small mistake. It will be plus. Here it was minus. Here it is minus. Minus minus become plus. It will be plus. Okay. So now how it is coming? So I can say that U double dash X plus omega square rho divided by E into UX, that is equal to 0. Can I say this? Now what is U double dash X? What is the meaning of this? Have a look. So this means nothing but second derivative of U in terms of X. So this is second derivative of U in terms of X. Then this is, how can we solve it? So is it a, what type of equation? It's an ordinary differential equation. Very good. So what can we assume? What is the order of that? Second order. So it's a second order ordinary differential equation. Perfect. This is second order ODE, ordinary differential equation. So what should be the solution of second order ordinary differential equation in this case? So what can we assume? Ux will be equal to summation of I equal to 1 to 2 AI e to the power of, or maybe j, aj e to the power of lambda jx, or in the simple word, if I write a1 e to the power of lambda 1x plus a2 e to the power of lambda 2x. There should not be any j. Sorry. Agreed? We can write like this way. And how we can get the lambda? We generally do not put this way the solution. We generally put the characteristics equation. So what we will substitute here? We will substitute here ux equal to a e to the power of lambda x If we substitute here e to the power of lambda x, so what will be u double dot x? That will be lambda square a e to the power of lambda x. Agreed? Perfect. If I just substituting this one, lambda square a e to the power of lambda x plus omega square rho by e a e to the power of lambda x should be equal to 0. Agreed? All of you? What is my objective to calculate from here? Lambda. Exactly. So now you can see that a can be cancelled out because a definitely cannot be 0, because if a is 0 then make no sense, that full thing will become 0. So a cannot be 0, e to the power lambda x also cannot be 0, so I am just cancelling it out. So I can say that, so what will be lambda square? Lambda square will be equal to minus omega square rho by e into this. So lambda will be equal to plus minus I times root over of e by rho times omega bar. So what is your solution now? Now your solution will be becoming u of x equal to a into e to the power of plus minus I, not like this way, because it has a two roots, we already know. So we should write it in the previous manner. So a1 e to the power of I rho e omega bar x plus a2 e to the power of minus I rho e omega bar x. Got that? How can we go ahead? So this way we can write it. Now see, very important point. Here it is e to the power of I something. That means what? No. E to the power I means it is sine cos. Sine cos, it's a harmonic term. And think, your displacement field should also be like a sine cos type. They cannot be decaying type thing. Got that point? So we can able to have our equations like this way. So here also, if you are interested, you can do it after that, like so. So you can think that this is now a1. So if I just say that this portion is like, let's say beta. So you can say that e to the power of I beta x plus a2 e to the power of minus I beta x. Okay, fine. Then next thing, a1 cos beta x plus I sin beta x plus a2 cos minus beta x, or sorry, not cos minus beta x. That is not wrong, cos minus beta x. That is the exactly correct. That is cos beta x minus I sin beta x. So what can I write from here? This can be written as a1 plus a2 cos beta x plus I times a1 minus a2 sin beta x. So you can also say c1 cos beta x plus c2 sin beta x. So these representing your displacement field in that complete thing. Okay. Now what do we want? We want our stimulus matrix, that if we are putting the force in one side and another side, how that displacement field and the force are connecting each other. So we got the displacement field. That is very nice. How we can able to get that other portion? So in the displacement field, if we think that if we try to get the proper displacement field or exact displacement field for that system, we also need the boundary condition, because this is steady state vibration, so we do not need the initial condition. But if we try to solve it exactly, we need initial condition. Then from initial condition it will go in the transient state and then it will come to the steady state. But we are just taking the steady state solution only, so we are ignoring that initial condition part. Like in time domain, we are not looking into, we are just simply saying that time domain the solution is harmonic. That's why if you see, we have substituted here the harmonic solution. We have substituted already, so we are only taking the steady state part. We are not considering the transient part. Agreed? But boundary condition we have not involved, and the forces that are applied on the boundary, that has to be considered here. Now we need to check how the boundary condition can be come into picture. Very good. So now if you think, we have this equation of motion. So here the forces are like F1, F2, or you can say like F0 and FL. That is the force direction for which we have written our equation of motion. So that direction of force gives me this form of equation. So this domain equation is actually representing this direction of forces. Okay. So now at boundary, if I try to think how much is the reaction force, so my Ux is coming what? You can write either of that, like A1 into e to the power of beta x is also okay, or you can write, which one you would you like to write? Which one? Please tell. Bottom one. Chalo, no issue. So C1 cos beta x plus C2 sin beta x. This looks better. No complex terms. Sin cos is much more familiar. Okay, no issues. And beta is what? Beta is root over of rho by E into omega bar square. That is root over of rho by E into omega bar. That is my beta. So now in beta already we can see the frequency term is present. Whatever is the excitation frequency, that frequency term is present into here. Okay, so this is my Ux. Now from here, if you think that if I try to find out how much force is applied, how we have calculated that force application? That force was from the strain. So if you see here, that force was from the strain, like F equal to EA into this into del U del X. That was my force. So force is, so force Fx is EA into del U del X. We have already derived that, because area into stress, stress is equal to Young modulus into strain, strain is nothing but del U del X. So this is E into A into del U del X. Okay, now U is this much. What will be the del U del X? So EA, then del X of C1 cos beta x plus C2 sin beta x. So what can we get? EA, then cos beta sin beta x C1 plus beta cos beta x C2. Agreed, all of you? Awesome. So if this is the scenario, then what will be, so that is my force, no problem, I get my force here. Now if you think force at this side and force at this side and displacement at both the sides, so displacements are looking like this, u0 and ul. Okay, how can I write u0 and ul? My u0 will be cos beta 0 into c1 plus sine beta, or else what can I do, right? I can try to write it in a much better manner. No need to write like this way, rather I can write it like u of x can be written as cos beta x sine beta x c1 c2. Agreed? And fx can be written as ea beta into minus sine beta x into cos beta x into c1 c2. Agreed? Agreed? So what will be, if I say my D vector is like u0 ul, then what will be coming here? Cos beta 0 sine beta 0 cos beta L sine beta L with c1 c2. Agreed? And what can we get here? Okay, that way we can get. Agreed, all of you? Now see, very simple. What is cos beta 0? One. Sine beta 0 cos beta L, cos beta L will be cos beta L. And this one minus sine 0, that will be 0, no need of minus. Cos 0 will be 1 minus sine beta L into cos beta L with c1 c2. Agreed? So that is my F matrix. But here if you see that we can try to do two things. One thing is what? If we try to write the stiffness matrix, then we need the force and displacement both in the same direction. Like if this is my u0, or maybe I should write it u1, u2, f1, f2. Okay, but if you see currently what is happening, my u0 is in this direction, my ul is in this direction, but my force, this is in this direction and this force is in this direction. Just have a look. Okay, so all the things are okay except this guy. So what we need to do? So we have seen that. So if I try to map like U0 UL to U1 U2, it will be just same. So I can just simply change it like U1 U2 will be equal to C1 C2. How it will come? 1 minus 1 0 cos beta L sin beta L. 1 0 cos beta L sin beta L. Straightforward, not a problem. Next one, how will that be? F1 F2. Now you think 0 1 this. Now here F1 will be changed. F0 need to be multiplied by -1 so that it can be changed. So these two will be changed. So here how it will be changed? So EA beta 0 -1. Previously it was 1. Now I have to put -1. Minus sin beta cos beta. Minus sin beta L into cos beta L, that is with C1 C2. Now if I try to write the finite element matrix, what is my main goal? My goal will be to write F1 F2 in terms of K into U1 U2. That K is my finite element matrix, terminus matrix. Agreed, all of you? So if I try to go there, how can I go? What I have to eliminate? C1 C2. Exactly. That C1 C2 is very much unwanted, and C1 C2 is also dependent on what is the amplitude of vibration and all those things. So we have to primarily remove that C1 C2. Okay, how we can remove it? Not a big deal. Take the inverse. Simple. So I can say F1 F2 will be equal to E. Just a minute, I have to write it much clearer. EA beta 0 -1 minus sin beta L cos beta L into this guy, that is 0 1 cos beta L sin beta L inverse U1 U2. Okay, how to do the inverse? Suppose if we have a matrix A B C D, what will be the inverse? AD minus BC, and this one will be A C B D. So EA beta into 0 -1 minus sin beta L cos beta L. Wait, now this will be sin beta L, 0 is 0, now A into D, sin beta L, this is minus cos 0, so sin beta L. Agreed? So now if I just multiply it, so 0 sin beta L minus cos beta L, so that will become cos beta L. This into this, so 0 1 minus 1 minus sin beta L, so that will be minus sin square beta L minus cos square beta L. So this will become cos beta L. So this is nothing but UA by B sin beta L, and this guy nothing but minus sin square beta plus cos square beta. So sin square beta plus cos square beta, that means 1 minus. So this is nothing but -1. Okay. So what can I say? cos beta L minus 1 cos beta L u1 u2. So that is my stiffness matrix. EA beta L divided by sin beta L in the cos beta L minus 1 cos beta L into u1 u1. Okay. Now, so what is frequency dependent? Beta. Exactly. So, what was the beta? Just let me check it quickly. So, root over of rho by E into omega bar. Okay. So now, if I put omega bar equal to 0, can I get the static frequency? Then whatever we made here, that should match, or that should come equal to the static frequency. Will that be happening? So this is my stiffness matrix, and beta was rho by E into omega bar. Okay. Now, if you think the static case, omega bar is equal to 0. So beta should be equal to 0. Or I should say like omega tends to 0. Because exactly if you put 0, then what will happen? Sin beta L becomes 0. Something like 0 by 0 type of thing will happen. Like here it will become 0. It will become 0. So it's like a 0 by 0 case. So let's not put it exactly 0. Let's just put it omega tends to 0. So tends to 0 gives us an opportunity to take some limiting conditions. So then it will be EA something like beta divided by sin beta L into, now think, once omega tends to 0, then beta also tends to 0. Okay. So what will happen? Cos beta L, that will be tends to 1. So this is 1 minus 1 minus 1 1. This portion is done. This guy. And here once we are taking it, so we should take a limit. Limit beta tends to 0. So if I put that limit beta tends to 0, so what will happen? Limit x tends to 0, x divided by sin x. How much is that? 1. So we can say EA divided by L look, this is the static stiffness. So this way we can see that once we are working with the dynamic case, we can able to consider that. Now here, please pay attention in the 2-3 important things. First and foremost thing is what? We have incorporated the mass and stiffness both into in the terms of beta, because beta has density as well as beta has Young modulus. So both the things is coming, or both the thing is flushed into the single expression, that is beta. Agreed? So now what this is the thing happening. So here you can think, once we are doing it like a finite element, we need to write the mass matrix, we need to write the stiffness matrix, both, and we have to solve it. But here the advantage is that you don't need to write the mass matrix, because in your dynamic stiffness matrix or spectral stiffness matrix, this is known as spectral stiffness matrix. So in that spectral stiffness matrix, the effect of mass is already included. So you don't need to write again for the mass. You can just directly solve it. Does that make sense? Additionally, We can also solve the natural frequency of the structure from this. How? For solving the natural frequency, we need what? Boundary condition. So we need to put the boundary condition here for solving the natural frequency. So suppose we are asking that let's solve for the bar having one side fixed or pinned, whatever, because that has only 1 degree of freedom. So fixed or pinned, like one side is fixed or pinned. So just to find out what is the natural frequency of that bar. So how we can do that? So we can say that this side, my displacement like u1 is equal to 0. Okay, and on other side your force is equal to 0. If I write that matrix here, F1 will be some value because F1 is the reaction force, so that has some value. So F1 will be some value, F2 is 0. Now I have EA beta by sine beta L into cos beta L minus 1 cos beta L into 0 times U2. U2 will also have some value. Like you think like a single degree freedom system, like you just have some displacement and you leave it. So you have just give some displacement and you leave it. Okay, so like this way the things is coming. So how we can able to solve that? We can write the last row of the equation. Wherever we found this is becoming 0, so that corresponds, and wherever it is non-zero, left hand side wherever is 0 and right hand side wherever is non-zero, that corresponds to this value. Agreed? Because if I write the last row, or maybe if I just write the last row, how it will be? It will be, or maybe I just write it in different color, maybe this one. So you can see that here if I write it, my F2 will become, or if I just make it like this one, like this is my F1, F2, this is K11, K12, K21, K22 times U1, U2. So F2 will become K21 times U1 plus K22 times U2. This is very sure. So these two will be multiplied with these two. Now what happened? The first one is 0. So this one is 0. So this has no contribution. Okay, and additionally what I know? This boss is also 0. So what happened? 0 is equal to minus 1 into 0 and this into this. So what ultimately left here? EA beta divided by sine beta L into cos beta L into U2. That is equal to 0. Now what can be 0 and what cannot be 0? U2 cannot be 0. Perfect. So U2 cannot be 0. EA cannot be 0. So what we left with? So we left with beta divided by sine beta L into cos beta L, that is equal to 0. And think, once we are trying to solve the frequency of the structure, what we are looking for? We are looking for omega. Where the omega is? Within beta. So we are basically looking for the solution of beta, nothing else. So what we can write it here? This one into quat beta L should be equal to 0. Quite interesting. Quat beta L, that should be equal to 0. So now we can also say that beta is not equal to 0. Because if beta equal to 0, that means omega bar equal to 0. So beta cannot be 0. So this also says quat beta L equal to 0. So what are the general solutions for quat beta L equal to 0? Yes. So beta L will be n pi by 2 possible. So what is n? Integer. Because here you have to understand one point, that if you recall that once we are solving a trigonometric function, we are not getting a single solution. We will get a multiple periodic solution. So they are periodically repeating multiple solutions. So we will get it multiple solution. So from here we can say what is beta? Beta will be nothing but n pi divided by 2L. So think what will be the omega bar. Now if you substitute all those things here, so you will have omega equal to n pi divided by 2L into root over of E by rho. You got that? So this will be my omega. So first mode, second mode, third mode, all the modes we can get like that. Okay, maybe we can leave it here. And then in the next class, I will show it from like how we can make the finite element and all those things from here. Okay.